So here we are doing the second part. Cameron's here with me, so he may ask a question every once in a while. Okay, so, oh, shoot. Sorry about that little delay. Oh, why is it not working? There we go. All right, my pen wasn't working, so here we go. The ionization energies for element X are listed in the table above. On the basis of the data, element X is most likely to be. So I want you to notice these ionization energies. You got 580, 1815, 2740, huge increase to 11,600, and then 14,800. So you would expect there to be a huge increase in ionization energy after you've removed the easy electrons, the electrons that are fairly easy to remove. So in this case, how many electrons were easy to remove, relatively speaking? This one, easy. This one, easy. This one doesn't take much more energy to take the third one away, but the fourth one takes almost 4 times as much energy. So given that, you're looking for an element that has how many electrons in its outer shell? Some element X that has 3 electrons in its outer shell, because those 3 electrons come off pretty easily. So that means that you're looking for one of these with 3 electrons. Sodium has 1, magnesium has 2, aluminum has 3 electrons in the outer shell, so your answer here would be aluminum.
How would you know that?
Because I know that there are 3 electrons that came off easily. By that, this is the amount of energy that it takes to remove an electron.
You count how many
small energies there are.
Okay.
So, and then with the fourth, to remove the 4th electron, it took a whole boatload more.
Because it can only hold 5?
No, they could hold as many as it wanted to, but if the huge increase that you saw, like suppose you had 100 for the first energy, then 200 for the second, and then 300 for the third, then 450 say, and then 5,000, you'd know there were 1, 2, 3, 4 electrons that came off relatively easy, and the 5th electron took a whole boatload of energy to get it off. So you know that there must have been some element X with 4 electrons in its outer shell, because they came off easy, and it's the outer shells that come off easily.
So then, in that case scenario, you'd be left with 1, 2, 3, 4.
I'd have none. If I took away these 4, there'd be none in the outer shell.
Yeah, but you got 4 missing.
Yeah, you'd have 4 missing. That's right. So in the oxidation state would be positive 4. Okay, now down here, which one represents a pair of isotopes? Isotopes have to have different numbers of neutrons. So let's just define those. Same element, but different neutrons. All right, so in this case, you can tell that number 1 is not the answer, letter A, because there's an atomic number of 6 and an atomic number of 7. They had, in order to be the same element, they got to have the same atomic number. Okay, down here, the atomic number is 6 and 14, so that doesn't work either. 6 and 14 doesn't work. All right, this is your pair of isotopes, because the atomic number is the same, but the mass number is different. So in this particular element, if I did protons and neutrons, they'd have, the first one would have 7 protons and 6 neutrons. The second one would have 7 protons, and Cameron, how many neutrons would it have?
14.
14 is the protons and neutrons, so you'd have to take away the protons, so it would be what?
7.
Yeah. Okay, so what makes them isotopes is that they have different numbers of neutrons, but they're the same number of protons. So they're the same element. They just got a different mass because their neutrons are different. So the answer is D. Okay, so now we want to look at this, these atoms that are in the ground state. And we want to get the atom that contains 2 unpaired electrons. So to do that, I think it'd be easiest to do this with dot diagrams. So let's draw the dot diagrams. We'll start with bromine over here. So we'll start backwards. So bromine has 7 valence electrons. So it'll be 1, 2, 3, 4, 5, 6, 7 valence electrons. Antimony, Sb, has 5 valence electrons. Now you'd have to look at your periodic table to know that, and I didn't pull one up. But if you look at antimony, antimony is number 51. It'll have 5 valence electrons. Gallium, it has 3 valence electrons. Calcium has 2 valence electrons. Sulfur has 6 valence electrons. All right, so which one has 2 unpaired electrons?
Bromine? The Br?
I see.
Wait,
I
two
only see,
unpaired?
yeah, 2 unpaired.
Oh, so one that don't have a side in general. Let's say GA? No.
GA has 1 unpaired electron.
Wait, so just 2?
Here's the unpaired electrons. There's 1, there's 1, there's 1. That's 3 unpaired. This has 1 unpaired.
Oh, so the
That doesn't
sulfur,
have any
the
unpaired.
sulfur.
So sulfur is your answer. It has 2 unpaired. So that's sulfur.
Wait.
Now the atom that contains only 1 electron in the highest occupied energy sublevel. So the answer is right in front of us. Which one is it?
You say it again?
Only 1 electron in the highest occupied energy sublevel.
SB?
SB has 3 electrons. So
What?
that would be the S sublevel.
One
Sorry.
electron in the highest energy sublevel?
Remember, P sublevels have 3 orbitals. So one side represents the S and the other 3 sides represent the P. So we're looking for something with 1 electron in the highest occupied sublevel.
I don't know. Tell me. Is it BR?
There's S. Okay, this was not gotten. That was what was that? Oh, that was antimony. So there's S right there. I'll put a box around the S electrons. That might be easier to understand. Whoops. Here's a box around the S electrons. Looks to me like they're all paired. Aren't those all pairs of electrons?
Yeah.
So which one only has 1 other electron besides those paired electrons?
A GA.
Yes, so the answer is GA. All right, you can. The easiest way to do this with dot diagrams, but then you have to know that that is that the other 3. These are the S's and those 3 are the P's. Another way to think about it, I guess, would be to do this. You could write the electron configuration for gallium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. So you can tell that the P sublevel has those 3 orbitals. It's just going to have 1 electron all by itself, unpaired. One electron in the highest occupied energy sublevel. Right there it is.
I can tell that by looking at the periodic table.
You can tell by looking at the periodic table too, because gallium's the first element in the P sublevel block.
So are they gonna give me a periodic table on the?
On the AP test, you'll have a periodic table. It won't have anything on it except mass and weight. And
Yeah, but couldn't I still
but you'll
get
be
the-
able to see it. Yeah.
Yeah.
That's why it's important to understand the trends. Okay, number 17. These are 3 species. Following groups are the 3 species. When which of the following groups are the 3 species isoelectronic? That is, they have the same number of electrons. I'm surprised they told you they have the same number of electrons. All right, so you're looking at, in this case, I just do them in a row. So I'll do protons and electrons. Maybe how am I going to make this clear? I'm just going to erase that. Okay, so we're going to do protons for the 3 in a row and then electrons for the 3 in a row. Here we go, like this. All right, this won't be real neat. Okay, sulfur has 16 protons and 18 electrons if it's got a -2 charge. Potassium
That's
has
18?
19 in protons and 18 electrons.
That's 18 right there.
Yeah, this is not very clear. And the answer is, the first one's the right answer. And calcium has 20 protons and 18 electrons. You see, sulfur has gained 2 electrons, so 16 plus 2 is 18. Potassium has lost 1, so 19 minus 1 is 18. And calcium has 20, but it's got a +2 charge, so it's lost 2, and 20 minus 2 is 18. All right, so in case you're not happy with the way I made that look, so let's just take that away.
I'm kind of confused by the whole thing in general.
Isoelectronic just means they have the same number of electrons. All right, so looking at these 3, I'm going to do protons and electrons. So you're going to have protons, electrons. Okay, so I'm just doing A. So sulfur has 16 protons, but since it has a -2 charge, it has 18 electrons. Potassium has 19 protons off the periodic table, you know that, but it has a +1 charge. So normally it would have 19 electrons, but a +1 charge means it's lost an
18.
electron. Calcium has 20 protons, but it's got a +2 charge, so it's lost 2 of them,
This was,
so it's got 18 electrons. See how those are all the same? Isoelectronic. Just picking one other one to compare to.
so isoelectronic is when all the electrons are the same.
Yeah. So let's take a look at letter C. I'm just randomly picking another one. Okay, oxygen has 8 protons and it's got a -2 charge, so it'd be 10 electrons. But we already did the sulfur. We know it has 16 and 18, so there you see those are not isoelectronic, so that wouldn't be the right answer. They're not the same number of electrons. So none of the rest of them will work out. The first one did, so the answer is A. Okay, 14. As you go from sodium to chlorine, what generally decreases? That's not a very hard question. So what decreases? Radius. As you go from left to right, atoms get smaller. As you go from top to bottom, atoms get bigger. As they get smaller, their ionization energy goes up. Their atomic mass goes up as you go across, not because of any periodic trend, except just gets bigger. Electronegativity increases because the atoms are getting smaller, attracting electrons more. And then the maximum value of the oxidation number goes up then down. So you want to know just generally decreases. So answer is atomic radius. All right, and then the last question, the effective nuclear charge experienced by the outermost electron of sodium is different than the effective nuclear charge experienced by the outermost electron of neon. Let's draw a picture of this.
Yeah, I was going to do
So
something
here's
too.
So here's sodium and neon. Here's sodium, here's neon. So you got your first energy level, your second energy level, and your third energy level, but neon doesn't have enough electrons for the third energy level.
Why does sodium get a third energy level?
Sodium, see, has 11 electrons. So the first energy level just holds the 2 electrons and a 1s. But the second energy level holds the s and the p. So that's 8 altogether. Then the third energy level has to hold 1 more because sodium has 11 electrons. Okay, and then neon, it has 1s2 and 2s2 and 2p6 because it only has 10 electrons. So the question says, why is the effective nuclear charge of sodium different than neon?
This is bigger.
Well, it's bigger. That's right. So since it's bigger, it's got, you see, neon has 2 electrons here and 8 there, and sodium also has 2 here and 8 in the second energy level, but the outer electrons out there all by itself. Okay, so let's see if we can figure out the correct answer. We know that the sodium's less because the inside electrons are going to repel the outside electrons, but I haven't looked at their answers yet. Okay, so they say sodium has a greater density at standard conditions than neon. Yeah, that would be true, but that doesn't affect its effective charge. Sodium has lower first ionization energy than neon. That's true also. And sodium has a higher melting point. Oh wait, well, I'm trying to answer the wrong question. So the difference in nuclear charge best accounts for which of these conditions? So they want to know which of these things is caused by this reduced charge on this electron. And the answer to that one then would be one of our periodic trends. So sodium has a greater density. No.
Is it B?
It is B. Because the sodium will lose this electron a lot easier than neon would lose one of these. And that's because this electron has less effective nuclear charge acting on it. The reason it's less effective nuclear charge is because it's got these inside electrons repelling it.
Is it like shielded?
Yeah. We call that the shielding effect,
So it's shielded from
the nucleus.
no the oh yeah.
Because the nucleus would be pulling it in, but these guys are pulling it out. So in effect, they're shielding this electron from the positive charge that's in the nucleus.
But this one has less layers, so it's more likely to enter into the nucleus.
It says less layers, so these electrons are going to be held tighter. So it's got ionization energy to be higher. It takes more energy to remove an electron. And that's the end of that sheet. So we'll review that again on Friday, just take questions on it. We've got a few things we need to do about ionic bonding, and probably should review the light math just a little bit on Friday. So all that stuff is coming Friday.